Hello everybody, today we are going to be going over the Trunnion magnet barrel redesign project submitted by Eries. I'm Eric Obringer.
And I'm Caleb Kemp.
So a brief overview of Eries as a company. They were founded in 1942 in the city of Erie, Pennsylvania. Right now they employ over 1,000 employees globally with 12 wholly owned subsidiaries around the globe. Their main specialties are in magnetic separation, metal detection, and material separation that focus on industries such as mining, recycling, and food industries. So how does the Trunnion magnet barrel function? On the right side of the screen, you can see the overall system produced by Eries. The arch-shaped orange sections are the magnets, which attract any magnetic material that falls into the system. But what this does, the barrel in the center there is mounted to the discharge end of a ball mill, and as material flows out, there's a chance that the grinding balls from the ball mill can follow through with the material itself. So what this design does, it attracts any of those grinding balls that falls into the drum, and as it rotates, the magnetic material is attracted to those magnets, and once it reaches the terminus point, it falls into that central hopper chute in the center, and all the non-magnetic material remains in the bottom of the barrel and continues out the end. And the main point of this is to ensure that those grinding balls from the ball mill does not damage any of the systems farther down the material processing. So when Erie submitted this project, they also submitted a problem statement, which basically states that they want us to redesign the 116-inch Trunnion magnet barrel to eliminate the diagonal braces, which we will refer to as the stiffener gussets in the future, as well as ensuring that the new design can operate into an infinite life, which is roughly 2+ million cycles. So some of the constraints that our design team created from the problem statement include must operate into an infinite life, must support the mounting flange, must eliminate or optimize the diagonal braces or the stiffener gussets, must retain or improve original strength with the new design, and must be constructed of non-magnetic material so that it does not interfere with the magnets in the system. Some criteria that we came up with include maximize operation life, maximize strength/stiffness of the design, maximize manufacturability, and minimize overall cost. The design that we came up with was implementing a stiffener ring around the drum. So what this does is that it decreases the stress concentrations acting on the drum, and this initial design on the left side of the screen was mostly intended to see if the concept of a ring was viable, but what we found from this was that it was an inefficient use of material. It added a significant amount of weight, and its size hindered manufacturability. We learned that after talking to a local foundry in the Erie area, which they said to us that if it's over 10,000 pounds, they do not have the facilities to manufacture a ring of that size. After verifying that a ring design was a viable option for this redesign project, we realized that the profile of the design had to be optimized. To do this, we utilized ANSYS Workbench and their structural optimization feature, and we input the initial design on the barrel and ran it through various stages of optimization. And what this does, it calculates all the stresses acting on the barrel and the design itself to determine what volume and what mass can be reduced while keeping the critical geometry in reducing stress concentrations on the drum. So as you can see on the left side, we had the initial 12x12 profile of the ring, and using the ANSYS optimization, it took it all the way down to the final design, which is shown on the right side of the screen, and it is a much smaller and more streamlined profile. Here we have the final design that the group came up with. As I mentioned on the previous slide, utilizing structural optimization led to a significantly smaller profile, but it also decreased the overall segment length of the ring, and now the final design is more of a stiffener block rather than a stiffener ring, as shown in the top right part of the screen. And in the image to the left of that, you can see the block installed on the drum. But putting this design back into ANSYS Workbench, we determined that the overall equivalent stresses were over halved of the original design. As you can see on the bottom, this new design had a total equivalent stress of 611 psi, whereas the original design with the stiffener gussets had a maximum equivalent stress of about 1300 psi.
Once the team came up with a final design, we did an integration check to ensure that all our new design would not interfere with the original barrel that Erie's provided us with. The first thing we checked was to make sure that the top of the stiffener block would not interfere with the bolt hole pattern, which, as you can see on the right hand side of the screen, is about 12 inches away from the bolt hole pattern. We also did a modal analysis and a fatigue life analysis to ensure that our new design would reach the infinite life, which is plus 2 million cycles. It's important to do a modal analysis on any kind of rotating machinery. The team did a modal analysis on the redesigned barrel and found that the natural frequency of the barrel ranges from about 81 Hertz to about 92 Hertz. Then the team compared these frequencies to the frequency of the barrel which it rotates at, which is 11 RPM, which is fixed based on the speed of the ball mill. We then compared the two results and found that there is about a 200% difference between the two results, which tells us that there's a very low chance that resonance would occur, which also tells us that the barrel will rotate smoothly without any issues. So the team did a fatigue stress analysis on the barrel to ensure that the barrel does have infinite life. We used FEA to gather our principal stresses and utilize the same procedure that Erie's uses when determining fatigue stress. We found that our redesigned barrel does in fact have infinite life, which is about plus 2 million cycles. So next, the team did a production cost estimate utilizing the original price of original barrel and the volume of the barrel. We were able to calculate an estimate of what our redesigned barrel would cost, which comes out to be about only a $200 increase. So here is just a simple cash flow diagram of the barrel's life throughout 10 years of its life. Every year, its estimated cost about $252 in operation / maintenance costs, and at the end of its 10-year lifespan, the scrap value would be about $3,700. So here's just a simple breakdown of a life cycle cost estimate over 10 years, assuming 4% interest. As you can see on the far right-hand side of the screen, those numbers are what the company would pay per year or gain per year based on the barrel. And after 10 years, the total cost of the machine for the lifespan would be about $82,000. Thank you for watching.